water may be in the fuel, may have water separators in place of the primary fuel filter. The use and regular maintenance of a water separator is highly recommended where water contamination of fuel is a common problem. Water contamination is not usually as big a problem in on-highway truck applications that use fuel from reputable truck stops with very high fuel turnover rates. It is more of a problem for applications fueling out of stationary tanks with lower turnover rates. Fuel stored for prolonged periods has a much greater probability of generating condensation. The number one cause of injector failure due to plunger seizure is ingestion of large quantities of water in the fuel. All diesel fuel contains some dissolved water, normally about 0.1% by volume. We're not talking about this quantity of water. We're talking about large concentrations, in pints, quarts, or gallons, generated from condensation or tank leakage. The film strength of the diesel fuel separates the metal surfaces of the injector plunger and barrel. When the film is penetrated, metal-to-metal contact occurs between the plunger and barrel, resulting in plunger seizure and injector failure. Water has a much lower film strength than diesel fuel. Large quantities of water provide very poor plunger lubrication and film strength and lead to injector failure. Some styles of aftermarket combination fuel filters and water separators recommend removing or bypassing the factory-installed secondary fuel filter. Removing or bypassing the 2-micron secondary filter is not recommended by Caterpillar. The use of aftermarket filters, the use of competitive brand filters, or even bypassing the factory secondary filter does not void the engine warranty. However, the warranty on fuel system components does not cover abrasive wear from improper filtration, unless a defect in material or workmanship is found in the fuel system component. Over time, abrasives in fluids can cause significant wear to even the most durable objects. Proper filtration is an essential factor in the life of all fuel system components. The fuel transfer pump is a gear pump that pulls fuel from the tank and pressurizes it to supply the injectors. The pump has an internal relief valve that controls maximum system pressure between 60 and 125 psi, depending on engine model. The hand priming pump, located on the filter base, contains a check valve that allows pumping fuel around the pump gears. The transfer pump is not serviceable. Replace as a unit if it can't produce adequate pressure. Always check the service manual for the correct pump pressure specification. Most fuel transfer pumps are located on the lower left side of the front cover. They may be mounted on either the front or the back of the front cover, depending on engine arrangement and packaging considerations. The fuel filter base provides a mounting stud for the spin-on fuel filter and also contains the hand priming pump and a valve to bleed air from the system after filter changes. The priming pump and bleed valve provide a means to fill new filters with fuel and purge air from the low-pressure fuel system. Caution: never pre-fill the fuel filters at installation. Pre-filling bypasses the filter element and introduces dirt into the system. This practice alone contributes to premature system wear. The final component in the low-pressure fuel system is the pressure regulator valve. This valve is located on the outlet end of the cylinder head fuel supply passage and is a normally closed pressure relief valve. There are two styles of valves used, 3406E and C10-C12. The 3406E regulator has a simple spring-loaded pressure relief valve that only opens when fuel pressure reaches the relief pressure setting. The C10-C12 style valve has a spring-loaded poppet with two orifice holes in the end. This valve allows fuel to return to tank at a rate of 4 liters per minute assuring adequate bypass flow and injector cooling. The pressure regulator valve also acts as a spring-loaded one-way check valve. The valve opens at 60 psi to allow excess supply fuel to return to the tank. When the engine is off and supply pressure drops to zero, the valve closes, preventing fuel in the head from draining back to the tank. While these valves differ slightly in design and operation, they serve the same purpose. EUI injectors take low-pressure supply fuel and pressurize the fuel between 10,000 and 30,000 psi. A camshaft-operated rocker arm pushes down the injector tappet and plunger, supplying the mechanical energy required to pressurize and pump the fuel from the injector. The combustion chamber receives pressurized fuel in the correct quantity and at the correct injection timing. The extremely high-pressure fuel flow through small orifice holes in the tip causes the fuel to atomize into microscopic droplets that burn more completely. This improved combustion more efficiently uses the heat energy of the fuel, resulting in improved fuel economy and reduced exhaust emissions. The low-pressure fuel system supplies fuel from the tank to the injectors. This system has three basic functions: to supply fuel to the EUI injectors for combustion, to supply extra fuel flow for cooling of the injectors, and to supply extra fuel flow to remove air from the system. The major components in the typical low-pressure fuel system are the vehicle fuel tank, the fuel transfer lines, the primary fuel filter or water separator, the fuel transfer pump, the secondary fuel filter and priming pump, and the pressure regulator valve. There are often component differences between the fuel tank and transfer pump on different engine arrangements and applications. For example, the recommended arrangement for most truck engines utilizes a 15 to 30 micron primary filter to catch large debris from the fuel tank. However, some truck manufacturers do not install a primary filter and instead rely solely on the secondary filter. Fuel drawn from the tank flows to the primary fuel filter or water separator. The primary filter screens large debris before the fuel flows to the inlet side of the fuel transfer pump. This is a simple gear pump containing an integral pressure relief valve. Fuel pressure is typically limited to between 60 and 125 psi. Excess fuel flows from the pressure relief valve on the outlet side of the pump through an internal passage to the inlet side of the pump. Fuel flows from the outlet port of the transfer pump to the secondary fuel filter. In the past, secondary filters typically had 10 to 15 micron ratings. Most 1999 and newer engines use 2 micron fuel filters. The 2 micron filter removes the very small abrasive fuel contaminants which cause premature wear out of the injectors. The fuel filter base also contains a hand-operated fuel priming pump. The purpose of the priming pump is to refill the system with fuel and remove air from the low-pressure fuel supply system after a filter change or injector replacement. The priming pump pulls fuel from the tank, around the transfer pump, and into the filter. It then pushes fuel through the supply passage in the cylinder head and back to the tank. Fuel flows from the secondary fuel filter to the supply passage in the cylinder head. On the 3406E, the fuel supply passage is a drilled hole extending from the front to the back of the cylinder head. On the C10, C12, a manifold on the side of the engine supplies fuel to each injector and returns excess flow back to tank. Excess fuel flows into the fuel pressure regulator. The fuel pressure regulator consists of a spring-loaded check valve. This pressure relief valve opens at approximately 60 psi and regulates pressure in a range of 60 to 125 psi. When the engine is off and no fuel pressure is present, the spring-loaded check closes to prevent the fuel in the cylinder head from draining back to the tank. Retaining fuel in the head maintains a supply of fuel for the injectors at engine startup. Most 1999 and newer EUI engines use a new electronic control system. This state-of-the-art system has many features and benefits. Although this presentation focuses on major electronic engine component operation, some basic electronic diagnostics are covered in the diagnostics portion of this presentation. The electronic control system consists of three types of components: input, control, and output. Sensors constantly monitor engine operating conditions and relay that information back to the electronic control module. The ECM is the computer that controls the engine. It has three main functions. It provides power for the engine electronics. It monitors input signals from engine sensors, and it acts as a governor to control engine RPM. It also stores engine operating information such as faults, events, and cumulative operating hours. The personality module is the software in the ECM, which contains the specific maps that define power, torque, and RPM of the engine. The ECM sends electrical currents to output devices to control engine operation. The heart of the electronic system is the new electronic control module. This powerful, state-of-the-art computer controls all engine functions, providing excellent performance and fuel economy while meeting stringent and ever-changing exhaust emission standards. The ECM provides many electronic features, including full authority electronic engine control, logging of engine faults, improved electronic engine diagnostics, electronic cruise control, programmable electronic PTO, engine monitoring and protection, and more than 100 programmable features. The new ECM has two 70-pin harness connectors, the engine harness connector and the vehicle harness connector. Older engines used an ECM with two 40-pin connectors. The engine harness connects the ECM to all of the sensors and actuators, including the EUI injectors. The vehicle harness connects the ECM to the engine control portion of the main vehicle harness. This includes the accelerator pedal position sensor, vehicle speed sensor, transmission, brake and clutch switches, cruise control and PTO control switches, data links, check engine and warning lights, engine retarder switches, speedometer and tachometer, and cooling fan solenoid. This wiring may seem complicated, but it's really quite simple. All of it is made up of many simple circuits. We will cover some of these circuits in the electronic system operation portion of this presentation. Sensors are simple electronic devices that detect and convert a change in pressure, temperature, or mechanical movement into an electrical signal. There are four basic types of sensors: pressure, temperature, position, and speed. A pressure sensor measures changes in pressure and sends a variable DC signal voltage back to the ECM. Pressure sensors have three wires. The first wire supplies voltage from the ECM to the sensor, providing power for sensor operation. This supply voltage is precisely controlled to 5 plus or minus 0.5 volts. The second wire is a ground wire from the ECM to the sensor that provides a 0 volts reference. The third wire is a signal voltage from the sensor to the ECM. This signal voltage varies with changes in the pressure of whatever the sensor is monitoring. The operating range of the signal voltage is slightly greater than 0 volts and slightly less than 5 volts. A typical operating range for signal voltage is 0.5 to 4.5 volts. The ECM also determines if a sensor is shorted or open by monitoring the signal voltage. If the signal voltage is the same as supply voltage, the ECM knows the sensor or sensor circuit is open. If the signal voltage is zero, the ECM knows the sensor or sensor circuit is shorted. If the ECM senses either a short or an open circuit, it will indicate a fault for that circuit to assist in troubleshooting. The key pressure sensors on the engine are the boost pressure, atmospheric pressure, and oil pressure sensors. A temperature sensor measures temperature and uses only 2 wires. Temperature sensors change resistance as temperature changes. The ECM reads the resistance value and converts it to a temperature. The ECM determines if the temperature sensor is open or shorted by monitoring the resistance value. If there is a short, the resistance value is near zero. If the sensor circuit is open, the resistance value is very high. The important temperature sensors on the engine are the coolant temperature sensor, the intake air temperature sensor, and the fuel temperature sensor. The third type of sensor is a position sensor. An example of a position sensor is the accelerator pedal position sensor. This sensor monitors the position of the accelerator pedal and converts that position into a pulse width modulated signal that is sent back to the ECM. A position sensor has 3 wires. The first wire supplies voltage from the ECM to provide power for sensor operation. The supply voltage for the accelerator pedal position sensor is 8 plus or minus 0.5 volts. The second wire is a ground wire from the ECM to the sensor that provides a 0 volts reference to the sensor. The third wire is a signal voltage from the position sensor to the ECM. The accelerator pedal position sensor generates a pulse width modulated signal, which is a square wave. A square wave is either full voltage or 0 voltage, on or off. Duty cycle is the percent of on time. The duty cycle for the low idle accelerator pedal position is between 10 and 22%. Duty cycle at the high idle accelerator pedal position is 75 to 90%. The accelerator pedal position sensor transmits this duty cycle signal to the ECM at a constant frequency. This type of sensor provides a very accurate signal to the ECM with a smooth transition during acceleration and deceleration. The ECM determines if the accelerator pedal position sensor is faulty by monitoring the duty cycle. If the duty cycle is less than 5% or greater than 95%, the ECM will log an active fault. The fourth type of sensor is a speed sensor. The speed timing sensor has a permanent magnet and a coil of wire. A change in the magnetic field of the sensor induces a voltage into the sensor. The ECM reads the increase and decrease in voltage as a signal. As the camshaft gear rotates, signal teeth cast into the gear pass through the magnetic field of the speed timing sensor. The sensor generates a signal voltage as each timing tooth passes. The ECM counts the time between these signals to determine how fast the engine is running. All of the teeth are evenly spaced except one pair, which has an additional tooth between them. This additional tooth sends an additional signal, which indicates top dead center to the ECM. Because speed sensors use an internal magnet and coil to generate a signal voltage, they do not require a supply voltage from the ECM. They also use only 2 wires instead of the 3 wires used on pressure and position sensors. Newer engines use dual speed sensors, each with 2 wires. One is for the camshaft gear and the other is for the crankshaft gear. Older engines use a single 3-wire speed sensor for the camshaft gear. On the dual sensor system, the camshaft gear is used to determine injector timing during engine startup. After starting, The crankshaft signal is used because it provides a more accurate and stable timing signal. With the new dual sensor system, if a sensor fails, the ECM will log an active fault and the engine will continue to run. With the older single sensor system, the engine will not run if the speed sensor fails. In review, 4 basic sensors govern engine operation: pressure, temperature, position, and speed sensors. The electronic system